In this video, we will explore polynomial long division. So we'll start here with 6x cubed minus 19x squared plus 16x minus 4, all divided by x minus 2. And we'll focus at first mainly on the x. So our first question is x times what gives us 6x cubed? And that is going to be 6x squared. We're going to treat this just like long division of whole numbers that we did in previous years. So we'll take 6x squared and multiply it by x. That gives us 6x cubed. But we also need to take 6x squared and multiply it by this minus 2, which gives us a negative 12x squared. We then want to subtract, which involves changing all of the signs in our bottom line here. 6x cubed minus 6x cubed cancels to 0x cubed. And negative 19x squared plus 12x squared gives us a negative 7x squared. We can then bring down the 16x, just like we brought down the next place value in regular long division. And now we're going to ask ourselves, x times what number, or what value, gets us to negative 7x squared. And this value is going to be negative 7x. So above here we will write minus 7x. Negative 7x times x gives us negative 7x squared. Negative 7x times a negative 2 gives us a positive 14x. However, we want to change all of those signs, and the purpose of changing those signs is, remember, that we need to subtract, so it's kind of like distributing a negative. So our 7x squareds cancel. We have 16x minus 14x, which is 2x, and then we bring down the minus 4. And finally here we ask ourselves, x times what gets us to 2x? And that is a positive 2. So 2 times x is 2x. 2 times negative 2 is negative 4. And when we change the signs of everything in our bottom row and subtract, we're left with 0. So here we've completed our first long division problem. And from this division, we can make a couple of conclusions. One of them is that 6x cubed minus 19x squared plus 16x minus 4 is going to be equal to x minus 2 times 6x squared minus 7x plus 2. Okay, because when we divide, it's the backwards of multiplication. So if we take the very long polynomial on the left and we divide it by x minus 2, our quotient is going to be the trinomial. So we can continue to factor this until it has been factored completely, and that will give us x minus 2, and then we can factor the trinomial that we have, and when we do that, it will factor as 2x minus 1 times 3x minus 2. So this is that polynomial factored completely. Let's take a look at another problem so that we can practice dividing further. So here we will have the example is x plus 1, and we're going to see how many times that goes into x squared plus 3x plus 5. So our first question again is, what are we going to multiply by x in order to get x squared, because that's our first term. So x times x gets us x squared. And we always want to make sure that these line up above, not necessarily what they go into, but so that we keep our like terms the same. So notice the x to the first is going above that 3x because it is also to the first power. So x times x is x squared, and then x times 1 will give us plus x. However, we're going to change these signs so that we can subtract. So we have x squared minus x squared, that cancels out. 3x minus x is 2x, and then we'll bring down that plus 5. So now again, we'll ask ourselves, x times what gives us 2x? And that's going to be 2. So then we get 2 times x is 2x. 2 times 1 is 2. And then when we change our signs and subtract, we're left here with 3. And this is actually our remainder. Yes, we can have remainders here. So that is your remainder. Remember that this up at the top, what our answer here, remember the answer to a division problem is a quotient. That's not going to change here. Underneath the radical, we have the dividend. And then outside, we have the divisor, or what we are dividing by. Right, so let's take a look now at the division algorithm. And the division algorithm says if f of x and d of x are polynomials such that d of x is not equal to 0, and the degree of d of x is less than or equal to the degree of f of x, there exist unique polynomials q of x and r of x such that f of x equals d of x times q of x plus r of x. And this is going to relate some of those terms that we had from before. So f of x is your dividend. D of x is your divisor. Q of x is your quotient. And r of x is the remainder. Okay, and that's going to be where r of x equals 0, or the degree of r of x is less than the degree of d of x. So if the remainder r of x is 0, then d of x divides evenly into f of x. Okay, so that just means that d of x is a factor of f of x. Okay, so a couple of other things before we apply that division algorithm. Okay, so we want to write the dividend and the divisor in descending powers of the variable. So you want to start, that's like standard form. You want to start with the highest exponent and then decrease each time. And then we are going to insert placeholders with 0 coefficients for any missing powers of the variable. And I cannot explain to you just how important that this number 2 is, this inserting placeholders with 0 coefficients for missing powers of the variable. And I'm going to show you here in our next example why that's important. and how to do that. Okay, so if we notice in this next example, we want to take x cubed minus 1 and divide that by x minus 1. But here we have missing coefficients, so we're going to rewrite this. We need to make sure that somewhere we have an x squared and an x term in this particular function. So we're going to take x minus 1, that's our divisor, so that's going to be on the outside. And underneath, we'll have x cubed. And then here's where the placeholders come in. Okay, so we're going to add 0x squared plus 0x, and then our minus 1. And we're doing this because we need to make sure that we have all of those the powers of x accounted for, so we have to have those placeholders happening here. Okay, so now that we have our placeholders, we can divide just like we've divided our first example. So x times what gives me x cubed? Well, that's going to be x squared. X squared times x is x cubed, and x squared times negative 1 is going to give us negative x squared. We change our signs. Our x cubes cancel, and we have an x squared. And just so we keep everything straight, I'm going to bring down the plus 0x here. Okay, and again, we ask ourselves, x times what gives us x squared? And that's going to be a positive x. So here we have x times x is x squared, and x times negative 1 is negative x. We'll subtract, giving us an x, and then minus 1. So then we have x times what gives us x, and that's going to be 1, a positive 1 there. So we'll have x, and then positive 1 times negative 1 is negative 1. We change our signs, and it looks like both terms cancel, so we're left with 0. Okay. Let's take a look at another example. So here we're going to take 2x to the 4th plus 4x cubed minus 5x squared plus 3x minus 2. And we're going to divide that by x squared plus 2x minus 3. So the first thing we can do is rewrite our division. So the first thing we'll do here is we have x squared plus 2x minus 3, and that's going to go on the outside. And then on the inside, we have 2x to the 4th. Let's just real quick before we get started, check for all of our coefficients. So we have 4th to the 3rd power to the 2nd power to the 1st power, and then our constant term. So we're good here. We don't need any placeholders for this. So we have our plus 4x cubed minus 5x squared plus 3x minus 2. And then we can just go ahead and divide this like we've divided everything else. The only difference here is we have an x squared, so we're going to be dealing with a little bit more terms here. And that's okay. So x squared times what gets us to 2x to the 4th. So obviously we need our 2 and then x squared. So we'll put this above that negative 5x squared term. Remember, we want to keep our x squareds lined up. So 2x squared times x squared is going to give us 2x to the 4th. 2x squared times 2x gets us 4x to the 3rd power. And then 2x squared times negative 3 gets us negative 6x squared. And then we change all of our signs. And then notice here that not only does our x to the 4th term cancel, but so does our x cubed term. So So we'll have a 0x cubed here, plus x squared, and then we'll bring down the 3x. Notice here, what times x squared is going to give us x cubed, and that's going to be a 0x. I'm going to write this in a different color. I'm just keeping this here for a placeholder. We don't really necessarily need to have that again in our final answer. So this is going to give us 0x cubed, and then plus 0x squared plus 0x here. And then we can subtract, and that's going to cancel. So here we're left with x squared plus 3x, and then we bring down the negative 2. So x squared times what gives us x squared, and that would just be 1. So we're going to take 1 times x squared is x squared. 1 times 2x is 2x. And 1 times negative 3 is negative 3. And we're going to change all of our signs. And this leaves us with an x plus 1. So let's take a look here. This is how we're going to write our answers. And we have a couple different ways, but I'm just going to show you the main one that we're going to use. So the answer here is going to be 2x squared. We don't need that 0x. Okay, so we can just write plus 1. And then here's how we're going to write our remainder. Our remainder is what's left. So plus x plus 1 over what we divided by. So x squared plus 2x minus 3. And this is one way that you can write your answers. That's the most common way. So now that we've done quite a few long division problems, let's take a look at synthetic division. And synthetic division is essentially long division, but with synthetic division, we can step back and focus only on the coefficients of our terms. And when we do that, it kind of cleans everything up a bit, and it comes up with such a process that we can do this very quickly, very efficiently, and take up a lot less space. So synthetic division, in order to divide, and we can do this for functions that are not cubic, so functions that are not just to x to the third, we can do this for anything. We just chose an x to the third so that we had like a limited number of example points here. And we're going to divide that by x minus k. And so here's one thing you need to be very careful of, that this is in fact x minus k. So if you have something of the form x minus 5, then your k equals 5. But if you have something of the form x plus 5, then remember really that's x minus negative 5. So k here would be negative 5. So that's very important to pay attention to. So we have this setup going on here where we have k kind of up in this little box all by itself. So we'll highlight that. There's k. Okay. And then we're going to take our coefficients in order, and if we need placeholders, we need to insert zeros. That's still very important. So we're just going to take those in order and kind of go down the line. And then we go through this process of bringing down whatever our first term is, so bringing down our a, and then we multiply that by k, and it follows this pattern of it goes down, and then we go up on a diagonal, and then down, and then up on a diagonal, and then down, and then up on a diagonal. And then hopefully we'll have something that works out, but a lot of times 0 is our remainder, and that tells us one thing, and then if 0 is not the remainder, then our remainder is going to give us a lot more information as well. Something else to highlight is that synthetic division only works for divisors of the form x minus k. That is it. We cannot have a coefficient on x other than 1, and we can't use synthetic division when we have a divisor that is a cubic or a quadratic or anything that is not linear, a two-term linear factor. If we have something more like that, more like the last example, we are forced to use the long division process. So we've heard a lot about synthetic division. Let's actually take a look at synthetic division here. So we have divide x to the fourth minus 10x squared minus 2x plus 4 by x plus 3. And if you notice here, we have this reminder that we have this 0x cubed here because that's actually very important. Okay, so let's take a look. We'll set this up. We have up in our little corner, okay, we're going to put -3 because this is a plus 3. Remember, we have that the form of x minus k, so our k is actually -3. Then we're just going to take all of our coefficients in order, including the 0x cubed. So we have 1x to the fourth, 0x cubed. Now here's where it gets a little tedious, and you need to make sure you take all of your signs. So this is not really minus 10x. Remember, this is a -10. Then we have a -2, and then a +4. I'm going to put this line here, and then I always put a box. This is where our remainder will go. So the first thing we do is bring down the 1. Okay, that's always the first thing, or whatever that term is there, that number. We just bring that down. And then we're going to multiply the -3 times the 1, and that gives us -3. Then we add. So 0 plus -3 is -3. Multiply this by the -3 up top. So we get -3 times -3 is a +9. Add that to the -10. We get -1. -1 times -3 is a +3. -2 plus 3 is 1. 1 times -3 is -3, and 4 plus -3 is a +1. So what does this mean now that we have this this process finished, but this needs a meaning, okay? So we've divided in order to get a final answer, and here's what our final answer is. So notice that up here we had x to the fourth power. This is going to be our coefficients in order, starting with 1 less, our exponent being 1 less than it was when we started. So because we divided x to the fourth, this is going to be x cubed. So we have 1x cubed minus 3x squared minus x plus 1. And then we have our remainder. So this is going to be plus 1 over x plus 3, because that's what we divided by, x plus 3. So this is our final answer when we do synthetic division. And this is how it comes about. It always the exponent always starts at 1 less than where we started in the original problem. So we haven't done quite as many examples of synthetic division, and that's because we're going to do more while we apply the remainder and the factor theorems. So bear with me through this. So we have the remainder theorem. If a polynomial f of x is divided by x minus k, the remainder is f of k. So basically what this is saying is that we can use synthetic division to evaluate a function at a certain value. So let's take a look here. So use the remainder theorem to evaluate the following function at x equals -2. So that means that we're going to put -2 up in our little box. Check our exponents, 3, 2, 1, 0. So we're good there. We don't need any placeholders here. Then we're just going to take the coefficients in order. So 3, 8, 5, negative 7. And then we'll make the box for the remainder. Remember that we always bring down our first coefficient, so we bring down the 3. And then we have, multiply that by negative 2. So negative 2 times 3 is negative 6. 8 plus negative 6 is positive 2. 2 times negative 2 is negative 4. 5 plus negative 4 is positive 1. 1 times negative 2 is negative 2. And we are then left with a remainder of negative 9. So what this is saying is that we actually have a point at negative 2, negative 9. So if I substitute negative 2 in for x, I should get back negative 9. Now let's check this using substitution. So this is like the old way you would have done this, which, so we'll check f of negative 2. So we'll have 3, and this is negative 2 cubed plus 8 times negative 2 squared plus 5 times negative 2 minus 7. So we can substitute in negative 2 everywhere that we had it, and x, and then we can solve this. So this would be 3 times negative 8 plus 8 times a positive 4 minus 10 minus 7. This would be negative 24 plus 32 minus 10 minus 7. This would give us here negative 24 plus 32 would give us a positive 8 minus 10 minus 7, which becomes negative 2 minus 7, which is in fact negative 9. And while it may be more comfortable for you at this point to use the substitution method to come up with your value, it is going to be much more efficient, much quicker to use the synthetic division and to use the remainder theorem. As you progress through more advanced mathematics, your equations tend to grow and they get longer, and you start with higher exponents. So it's a lot more efficient to just be able to do that remainder theorem. It looks a lot cleaner too. So then let's take a look at the factor theorem. Let's see what that tells us. So the factor theorem says that a polynomial f of x has a factor of x minus k if and only if f of k equals 0. So if our remainder is 0, then x minus k is a factor. So we could have, in a way, factored that out. Again, when you get into more advanced mathematics and your functions get to be larger and larger, being able to just do a synthetic division problem can expedite your work and make your work go a lot quicker. So let's take a look at a few examples in the next video. All right, so here we're going to use that factor theorem, and we're going to show that x minus 2 and x plus 3 are both factors of 2x to the fourth plus 7x cubed minus 4x squared minus 27x minus 18. So the first thing I'm noting here is that in our f of x, we start with the exponent of 4. We have a 3, 2, 1, and 0. So we, again, do not need any placeholders. Remember, this is not always the case. So we're going to check x minus 2. And remember, because all of our factors are in the form of x minus k, that's actually a positive 2 that we're checking right now. Then we're going to line up with all of our coefficients. So we'll start with a 2, we have a 7, negative 4, negative 27, negative 18. And I just tend to put that little box there. So again, we'll bring down our first coefficient. Oh, that's a pretty messy arrow. So we have a 2. And then we'll go through the multiplication process. So 2 times 2 is 4. 7 times 4, or 7 plus 4 is 11. 11 times 2 is 22. Negative 4 plus 22 is a positive 18. 18 times 2 is 36. Negative 27 plus 36 is positive 9. 9 times 2 is 18. Negative 18 plus 18 is 0. So here we have a remainder of 0. And that's what we wanted, right? Was that remainder of 0. So we know that x minus 2 is definitely a factor. So is a factor. Okay? Because it had a remainder of 0. Now we're going to check x. We're going to check that x plus 3, which is really, remember, negative 3. But we're going to do this as a repeated thing going on. Because what this is saying, really, okay, hopefully this isn't too hard to read, I'm going to put it in yellow, is that f of x, and I'm not going to write the whole thing, but that's going to be equal to x minus 2 times 2x cubed plus 11x squared plus 18x plus 9. So if x minus 2 is a factor, then we know that that x plus 3, if it's a factor, is going to be a factor of this part of the polynomial right here. So we're actually going to do what we call repeated synthetic division. So we'll take our negative 3. Remember, it was x plus 3, so we want the minus there. And we're just going to worry about these coefficients. Okay? So we have 2, 11, 18, 9. And we're going to do that same synthetic division process here. So we bring down the 2. 2 times negative 3 is negative 6. 11 plus negative 6 is 5. 5 times negative 3 is negative 15. 18 plus negative 15 is 3. 3 times negative 3 is negative 9. And 9 plus negative 9 is 0. So again, we have 0. So this is saying that x plus 3 is indeed a factor. So again, is a factor. So now we can write f of x as x minus 2, x plus 3, and then this would be 2x squared plus 5x plus 3. A lot of times you're going to be asked to factor this completely, and yes, you could indeed factor this trinomial. And I expect you to remember how to do that at this point. So we have here, in closing for this section, uses of the remainder in synthetic division. So the remainder r obtained in synthetic division of f of x by x minus k provides the following information. So the remainder r gives the value of f at x equals k. So your remainder is f of k. So that's a very useful, quick tool to evaluate a function, especially a larger function. The second thing is that if r equals 0, then x minus k is a factor of f of x. So we don't have to worry about any remainders then. We know that that's a factor. And if r equals 0, so again, no remainder, and x minus k is a factor, then k comma 0 is an x-intercept of the graph of f. So this is also giving us a way to find x-intercepts of our polynomial functions. So it's actually very useful to be able to do synthetic division and then describe the graph using the remainder.